This is MASC 505, Wednesday, August 29, 2007.
Okay. By the way, for those of you on campus, in case you're wondering why I'm waiting, I have a little monitor here which shows what's being projected. So I got to wait till the end of the music before I start. For those of you who've been in band classes before, know. And then the projectionist will let me know when the class ends as well. The reason being, the class is being filmed for the people that are off campus. I ended the last lecture basically talking about the fact you can describe a crystal by giving the lattice and the basis. Let me just give another example. Suppose you have a lattice, which is a simple square lattice. That would be something that looks like this. And the basis, let's take it to be now a two-atom basis, where the two atoms are different. And to represent the two different types of atoms, I'll use one as a circle, and let's say one as a square. So if you take the lattice plus the basis, that will give you what the crystal looks like. So a crystal with this lattice and this basis will have, at every one of the lattice points, you have, the basis. So you have a circle and a square. Same here, over here, and over here. Okay, so every crystal can be described basically by giving, the lattice and the basis. Now, it turns out another way which you can describe the crystal, and this is usually the way they do it at an undergraduate level, and in some sense you might argue this is a lot simpler than what I'll be doing in this class, is simply to give the unit cell. And the unit cell is, you can think of it as a basic pattern. If you repeat the unit cell, you recreate the entire crystal. So this crystal, has this basically repeated, so I could simply take this as a unit cell. And if I describe to you that you have these four atoms in the corner, you have one more different atom in this position here, and just repeat itself, you'll basically recreate the entire crystal. And yes, in some sense, the unit cell is a simpler representation of a simple way of describing a crystal, and that's why they do it at the undergraduate level. But it turns out the problem with the unit cell is that it doesn't tell you what the symmetry is, and we need to know what the symmetry is for the reasons I mentioned in the last lecture. You need to really know symmetry, because that will tell you where the atoms are, which is what you want to do if you're doing diffraction. The other thing is that if you want to know what the properties are, that is, if you want the symmetry of the properties, I should say, that is determined by the symmetry of the crystal. And the unit cell by itself, and as if I just tell you, well, you have atoms these far apart and so forth, you would have to go back and say, well, what is the point group or space group in order to deduce that information? So you need that information. So admittedly, it's harder to describe by using point group and space groups. Nevertheless, it is a lot more useful than the unit cell representation. Unit cell, by the way, there are multiple unit cells that you can use to describe a crystal. To give you an example, it's not unique, certainly. Suppose you have a lattice, or you could say a crystal, I should say, that looks like this. you could describe this with a unit cell that looks like this, okay? And that's a valid unit cell. You repeat that, you repeat the entire crystal. But that's not unique. I could have picked something that looks like this. And that would work. My drawing's a little distorted, but you know, it would be a square. And you repeat that, and that would also recreate the thing. So there's not a unique description to the unit cell. And so you can try your clickers. I had a couple questions from the clickers. If you could switch to the laptop, and all of you have your clickers. Actually, Kiza, this is yours. Okay, don't lose it. Just bring it to class every day. Yeah. Is the operator back there? Can you switch to the laptop? Oh, do I have to do this? Hold on. I don't know if I'm... Let's see. Okay, try it now. It should switch over. I didn't put my output to the... And I want you to switch. You can switch the screen to the laptop. Oh, maybe that's... Oh.
Professor, someone is coming to check it out.
Okay. Actually, if you try it again, I think this cable was just the cable is loose. I think it should switch now. Actually, in some of the room I was in last year, you could switch it. Actually, here I just push it. So we'll see the. Okay, thanks. So, in case you weren't here on Monday, one part of this class I'll have the use of the clickers. It allows me to ask you questions, and I threw a few questions on the unit cell just to, well, so you guys can try out the clickers. Remember, you click in with the answer, and then you get a green light on your clicker, which indicates a response is received. So, if you take, for example, this one here, which one of these parallelograms you have, you know, A, B, C, D, and E, that is answers 1 through 5, are the unit cell for that particular crystal structure? And I count down, you got 30 seconds. Okay, most people chose number, actually, wait a minute, that's odd. What did it do here? It should add up to 100%.
All three, it's A, E, and D, isn't it?
Oh, repeat it again?
All three, A, E, and D are all unit cells, aren't they?
Right. But I mean, what I'm saying is the percentage. They should add up to 100%. That's the thing that's a little screwy.
I clicked twice.
Well, no, clicking twice shouldn't be a problem. Okay. That's an interesting question. Maybe I should just offer. My understanding was, you know, if you click, you can change your mind. So you can click. Well, suppose you answer 1 and you change your mind and you say it's 2 and you click again. It should only take 1 response. That was my understanding. Well, yeah. I mean, what Peter said was true. There are multiple answers to this, multiple correct answers. Either A is correct. This one shown here. Actually, hold on. My laser pointing. A is correct, the one shown here. D is also correct. I mean, you don't have to, take the ones at the corner. You can, that would certainly be fine. You don't have to have it in the shape of a square either. You can take this rhombus, and that's fine as well. Obviously, you take that and you repeat itself, your unit cell. B would be incorrect because it's too small. You're not going to repeat it. And the problem with C is a little too big. You're going to, not create the same pattern if you repeat that as a unit cell. I think I have another question. Yeah, this one here. Same question. This is actually a chemistry professor at Brandeis who threw that on his website. So nice thing about these questions, you can copy other people's question, and that's perfectly fine. So I took what he posted. It's kind of like a wallpaper pattern. But the question is, which one of these parallelograms? This is A, this is B, and this is C, our unit cell. Once again, this is not a test, so you can ask your neighbor. So. Okay, this one works fine. Yeah, well, we're evenly split between A and C. It turns out the correct answer is C. Why doesn't A work? Well, you might say, well, if you take, oops. What am I doing? Don't want to hibernate. Don't hibernate. I may have to bring in the power cord for this thing. The power cord, I think. Usually. Okay, the problem with A, as to why it's not a correct answer, is that you might say if you take this unit cell and you shift it over, that's fine because this head goes here and that head goes there. But the other thing, you also have to look when you shift it this way. When you shift it this way, it doesnn't work. You have a head this way, and if you shift it up, the head is pointing that way. So A actually doesn't work as a unit cell. It's kind of the way you check the unit cell. And well, in 2 dimensions, you shift it in both directions and make sure it repeats. In 3 dimensions, you shift it in all 3 edges and make sure it repeats. B doesn't work either for the pretty much the same reason. If you shift it down, it works fine. This head goes here and so forth. But if you shift this thing, let's say, to the right, you have a head going this way, the head is going this way, so that won't repeat. C is the only one where when you shift in both directions, it repeats itself. If you take this, you shift it up, that's fine. If you take this and you shift it over, it's fine. So C is the quote-unquote the only correct unit cell for this particular 2-dimensional pattern, not a crystal, but it's anything with a translational symmetry you can always define in terms of unit cell. Now, if I could go back to the smartboard. Thanks. Basically, if you take the lattice, another thing which you probably learned in an undergraduate class is that there are 14 Bravais lattices. And many of you probably know them from memory. You can repeat them for me. An interesting side note, by the way, with respect to the Bravais lattices, Bravais actually did not derive the 14, well, at the time they're called space lattices. The story behind it is the following. In 1842, there's a paper published by a German scientist, Frankenheim, and in his paper, basically, he did the derivation. He derived the number of space lattices that can exist. So we're talking about in 3 dimensions. However, he derived that there are 15 space lattices. Subsequently, a few years later, 3 years later, in 1845, Bravais, Auguste Bravais, published another paper, and the only thing that he did in his paper was that he showed that two of the lattices that Frankheim had derived were equivalent. So basically, Bravais basically showed there are only 14 space lattices. Or basically what he showed that two of the ones derived by Frankheim were equivalent. Subsequently, even though Bravais did not really do the derivation, he was quote-unquote the first one in some sense to do a derivation correct. His name is associated with the space lattices. So I mean, there's probably a moral to the story. You know, it's not who does it first; it's who does it first correctly that counts. Now the question is, which you probably never wondered when you're given these 14 Bravais lattices, is what makes a Bravais lattice unique? That is, how do you know there are only 14? And the answer, is basically what we cover in this class. It's based on the symmetry. And if you look at the symmetry, all of the 14 Bravais lattices have a unique symmetry. And basically, this is what Bravais did. He showed that two of the lattices, space lattices that Frankheim had derived, actually were the same. And you'll actually do that as a homework problem later on. I think it's somewhere in the second or third homework. I asked you to take these two space lattices and show their equivalent. Which is basically exactly what Bravais did. So, I mean, if you did this 150 years ago, your name could have been attached to it, but of course, it's already been done. So, and you'll see, it's not that difficult. It's just that you just got to recognize it. I mean, in some sense, the problem you're doing is a little easier than the one Bravais did, because I'm telling you these two are the same. Just show me which. What Bravais had to do was look at all 15 and make sure they're all unique, and that any pair of the 15s were not the same. So he actually, I mean, to give him credit, he solved a little more difficult problem than the one that you're solving. And this section is basically covering crystallography. And the crystallography basically is, if you were to define crystallography, it would simply be a classification which is based on the symmetry. So it's a classification of, let's see. It's odd. How do can I just start a new page, I guess, or can I just extend? Oh, what is it? Repeat that again?
The bottom, you see a little word that says extend page?
Yeah, I tried that. It doesn't work. That's what I'm... Oh, Chris, let's try it here. See, it has a... Gives me black one. Why can't I extend?
Top left is a little page with a plus sign on it. That's a
Repeat that. Page with a plus sign.
Over, other way.
Okay. Well, that puts another page. Okay. Well, I guess that'll work. I don't know. Maybe there's a limit. Is there a limit to how long I can make the page? I mean. Well, this will work anyway. So, basically, crystallography, I'll have to start all over again, but, well, for that. Crystallography can be defined basically as a classification of crystals based on symmetry. So rather than classifying things in terms of the unit cell or the Bravais lattice or whatever, what crystallography is we're going to look at the symmetry. And there's sort of two classification schemes. One is sort of like a more general, and the other is more specific. The more general one is what is called the point groups. And for the point groups, there are 32 point groups. And the 32 point groups, so what is basically 32 possible combinations of symmetry elements. Not including translation, or symmetry elements if you want, without translation. Translation is, as the name implies, you just symmetry or any type of symmetry element where you're simply translating it, moving it if you want to describe the symmetry. Now, you can also include, I don't want to go that far, you also can include translation, and if you do, you will basically have what is called the 230 space groups. So you have 230 space groups. Every one of these space groups, by the way, belongs to one of the point groups. And the only difference between the space groups is that you are taking the combinations of symmetry elements with translation. So there are 230 possible combinations of symmetry elements with translation. Now, of course, this raises the obvious question, why are you concerned with translation? Or maybe you should ask the question, why are you not concerned with translation, and why do we separate it? Well, it turns out if you're only dealing with the symmetry of the properties of the crystal, you only need to know the point group. You don't need to be concerned about any translation that exists. If you want to know where the atoms are located, that is, we want a description of the crystal, you need to know the space group. You need to know whether or not there are any translation involved. Why is that the case? Well, let me give you an example. Let's take a very simple symmetry element, a mirror plane, and operate upon it on a group of atoms. So suppose we have a group of atoms, and we're going to do this in even simply if you want in 1D. Suppose we have just 3 atoms in a row. And suppose we have a mirror plane. A mirror plane, let's say in this orientation here. In other words, to make sure the plane is perpendicular to the board, coming out this way. What this means, therefore, and sometimes I get a little bit ahead of myself because I haven't defined the symmetry elements. But a mirror plane is pretty straightforward. I think everyone knows what a mirror plane is. It's what happens when you look in a mirror. You get the same thing on the other side of the plane. So if you have an atom here, you would have an atom here. If you had one here and here. So this is a crystal which has a mirror plane symmetry here. Whatever you have on this side, you have the exact same thing on the other side. With respect to the properties, what it means is the following. Suppose we were measuring some property in, let's say, this direction here, and it makes some angle theta with respect to the mirror plane. This property could be, let's say, something like resistivity, any property. You get a certain value. Now, suppose you measure the property in this direction, where this direction is also at the angle theta with respect to the mirror plane. It's just, the mirror operation of this direction. I would argue that the property in this direction, let's call this direction 1, and the property in this direction 2 should be the same. That is, they're equivalent. And physically, the reason for that is the following. Suppose it's resistivity. You look at what happens when the electron is traveling in the crystal in this direction. Well, I would argue that's because of the symmetry, whether the atom is coming in this direction, the one direction, or whether or not the electron is going in the two direction, it'll see exactly the same thing. Because basically, if it runs into the atom here and so forth, on the other side, since everything is mirrored across, when you come in that direction, it'll see exactly the same environment, and therefore the property should be exactly the same. So you prove therefore that the directions, the property in the one direction and the two direction must be equivalent. Now, what happens if you add a translation? Well, actually nothing, and it's based on the fact that there's a simple principle that the physical properties are invariant with respect to translation. This are invariant, just a fancy way of saying it does not change. The physical properties, so basically, physical properties do not change with respect to translation. I mean, this is almost an obvious statement. What I'm saying, or what this sentence is saying is, you have a crystal, and you measure the property, say in this direction, and you translate the crystal. So you can move it up, you can move it down to the right or left, and you measure it again. Okay, and it should be the same, right? I mean, it's kind of an obvious statement that moving the crystal, anywhere in this room is not going to change its physical properties. If I rotate it, on the other hand, or do something other than a translation, yes, the property will change because I'm now measuring it in a different direction in the crystal. But with respect to translation, it has no effect on the physical property. So, based on this, the statement, you can show that, suppose you have a symmetry element which had a translation, an example of which is a glide plane. The distinction we make with respect to glide plane, we use a dashed line versus a solid line. So this is what is referred to as a glide plane. A glide plane is like a mirror, except in addition to mirror, you translate. So if you have, let's take the same three atoms we had before. If you have a glide plane, what happens is that this goes across to that position there. Then you translate. The translation can vary, but let's suppose the translation in this case was a half of the separation. So it comes down by here and produces an atom there. So a glide plane is basically a mirror plus what we call a parallel translation. By the way, I'm going to use this symbol here. This means parallel. Another symbol which I'll use, by the way, I'll use a upside down T for perpendicular. These are words we use all the time, so I don't have to keep writing the word parallel and perpendicular. The two parallel lines means parallel. So a mirror plus a parallel translation. Parallel translation meaning the translation is parallel to the mirror. This is what is called a glide plane symmetry. Now, if you operate upon it, what happens is this atom goes across, shifts down. This one goes across, shifts down. See, this goes across and shifts down. So it's kind of like the mirror symmetry, except these three atoms, instead of being right across, is shifted down a bit. Okay. Now, the question is, what sort of symmetry will the property have? Well, I will argue that the symmetry of the properties will be exactly the same as that of a mirror plane. That is, if I take a direction, let's say, again, which we'll call 1, and this direction makes an angle theta, then if I take this direction here, which is called 2, which makes the same angle theta, that 1 and 2 are equivalent. Now, why is that the case? You say, well, not really, because you say, you take the atom, and the atom coming in the one direction is going to see one environment. The atom coming in the two direction is not going to see the same environment because all these atoms are shifted down a bit. Okay. Well, that's fine. All we have to do is define a 2', where the 2' is in this direction here. So the only difference between 2 and 2' is I moved it down a bit. And I've moved it down, this distance here is some distance t, which is the same distance as we translated this distance here, t. And if I do that, then when I look in direction 1 and I look in direction 2', it should be exactly the same. Okay. So we know basically from the way we define the glide plane that 1', sorry, 1, I don't have a prime, 1 basically, and it is with respect is equivalent to 2', because it's defined by the way the operation occurs. However, the only difference between 2' and 2, they're simply translated with respect to each other. So we know from the other statement, if I measure the direction of the property in the 2' direction, and I measure it in the 2 direction, all I'm doing is moving the crystal, they should be exactly the same. So by that argument, 2 and 2' are also equivalent. That is, 2 and 2' are equivalent. And as a result, since 2' and 2 are equivalent, that 1, therefore, should be equivalent to 2. Okay. So 1 is equivalent to 2' because, the two directions are related by the symmetry operation. 2' and 2 are just simply translation of each other, so therefore they have to be equivalent. And as a result, you end up with the conclusion that the one direction, I don't know if we can, well, I like to squeeze it into here. So it means that 1 and 2 basically are equivalent. So this is why, in some sense, it doesn't matter whether or not you have a symmetry element which has a translation or doesn't have a translation with respect to any of the properties. So if you're concerned about the symmetry of the properties, that is, whether or not the property will be the same if you mirror across or you do any type of rotation operation, all you need to know is the point group symmetry. You don't really need to be concerned about any translation. So whether it's a glide plane or a mirror, it doesn't matter. Glide planes basically are treated like mirrors. That's why there are a smaller number of point groups. You don't need to distinguish. Which then raises the other question, well, why are you concerned about glide planes? Well, because if you have glide plane symmetry, you have 3 atoms here, then these 3 atoms are shifted. If you have mirror symmetry, you have 3 atoms here, and the other 3 atoms are right across. So where the atoms are located do change, okay, because of the translation, but they have no effect on the physical property. Because of the simple, idea, the simple concept, properties are independent of, of translation. So the rule, so to speak, is that the symmetry of the physical property of a crystal is determined by the point group. And that's why we need to know, the point group. On the other hand, the space group gives the location of the atoms. Which is another thing we need to do. And so in the second part, the first part we'll do with crystallography. That's the first third of this class. The second third of the class deals with the symmetry of the physical properties. That's the physical properties of crystal part of the class, and we'll do with point groups, which we will derive in the first part and apply them to the physical properties. And the last part of the class has to do with diffraction. If we give a crystal, you tell me where the atoms are, and that's basically a diffraction experiment to determine the space group. One thing which I'll mention at the outset, and in some sense this is sort of the key thing about the third part, is that each space group has a unique structure factor. Some of you know what a structure factor is. If you've had any elementary course in diffraction, that's kind of the first thing they do, calculate structure factors. If you don't, it's okay. I will cover that and derive how you calculate a structure factor. But it's based on where the atoms are located, and basically each space group has a unique structure factor. So if you can identify what the structure factor is, you can identify the space group and allow you to identify therefore where the atoms are located. So what are these symmetry elements? Maybe I should start a new page for this as well. There are three types of symmetry elements that we'll deal with in the class. The first one is the rotation axes. And for the rotation axis, it's given with a number, which for now I'll just call n. And what a rotation axis is that it's, as the name implies, you rotate. And you rotate by 360 degrees divided by n. So you have 5 different rotation axes. You have a one-fold rotation axis, a two-fold, a three-fold, four-fold, and a six-fold. Why only these 5? Well, it turns out you can't have a 5-fold or anything higher than a 6-fold because it's inconsistent with translational symmetry. Now you might say, well, didn't we agree we're going to ignore translational symmetry? Yes, we are, but we're still describing a crystal, and a crystal has to have translational symmetry. So there's no way you can have a rotational symmetry inconsistent with translational symmetry. And only these 5 exist. The one-fold, in some sense, is really null symmetry. Obviously, if you take any object and you rotate it by 360 divided by 1, that is 360 degrees, it's in the same orientation, so it's obviously going to be the same. What symmetry means, maybe I should define it first, is that if I do this operation, suppose two-fold, if I rotate the object, rotate it 180 degrees, it's completely unchanged. In a crystal, meaning the atoms are exactly in the same position if I rotate it 180 degrees. Three-fold, 120 degrees, four-fold, 90 degrees, six-fold, 60 degrees. If a rotation axis, as the name implies, this is a line, obviously, and rotation axes have orientation. You have to look in a particular direction to see that rotational symmetry. Now, in addition to rotation axes, the second thing that we have is the mirror plane. The symmetry, the symbol for the mirror plane is just M. And the mirror plane is, self-evident. Basically, is what happens when you have a mirror. If you have a mirror plane here, you have any object here at x, y, z. It mirrors across onto the other side. So suppose, let's say this is the let's define a coordinate. Suppose this is the x direction. If this is x, y, and z, this would be minus x, y, and z. Write this a little clearer. a notation, by the way, what I'm using here, this thing, that's minus x, okay? In crystallography, it's kind of inconvenient to put the minus to the left because, you know, if it's a minus y, you got to squeeze it in there. So we put the minus on top, okay? So the bar on top of the thing just means it's negative. So because of the fact that, you know, it's on opposite side, the only difference by mirror plane, it changes it by, you know, the sign. And the third symmetry element, and a mirror plane, by the way, is a plane, you know, and it has orientation. So obviously, it's mirrored with respect to, you know, a particular orientation. The third one is what is referred to as an inversion point. An inversion point, as the name implies, is a symmetry element, which is a point, and you simply invert. So suppose this is your inversion point, and so let's take this to be the origin that is at the 0, 0, 0 position of our yes. So if you have some point here which is at x, y, z, then the point on the minus x, minus y, minus z, these 2 points are equivalent. So you invert, if you want to turn everything inside out, the crystal will remain unchanged. Then it has an inversion point symmetry about a particular point. Now the key thing about inversion point symmetry is that this has no orientation. It's a point, right? A line has an orientation and a plane has an orientation, but when you have a point, it doesn't have an orientation. The significance, therefore, is that if you have a crystal which has an inversion point symmetry, you can't say, well, it has inversion point symmetry only when you look in this direction, but not in this direction. It just physically doesn't make any sense. If you have inversion point symmetry, you have it. Okay, so either a crystal has inversion symmetry or it doesn't have inversion symmetry. Those are the only two options. Okay, unlike a mirror plane and a rotation axis where you have to look at the different orientations to determine whether or not it has inversion, and whether or not it has mirror or rotation. Now, if you could switch back to the laptop, hopefully it's still running. I think it went to hibernation again. Never mind about the laptop. Go back to the smart board. I'm going to have to bring my AC adapter on Friday. I think the problem is I teach a class 11 to 12, which I also use a laptop, and I think my battery just can't stand 2 hours back to back, so I'll have to use the plug-in. Now, if you take the symmetry operations, you can actually define it into two types based on a concept which is called handedness. So, and it turns out it's important to know whether or not the symmetry operations have handedness or change handedness or do not change handedness. If you take a translation, which we actually haven't talked about, but we will in a minute, and a rotation axis, these do not change handedness. What I mean by that is the following. First of all, what is handedness? Handedness refers to the fact that you can have an object which is right-handed versus left-handed. A good example is actually your right and left hand. So your right hand, let's say, is one-handed, and let's call it the right-handed version. The left hand is your left-handed version. When you look at your right hand and you look at your left hand, they're very similar, but obviously your right hand is never the same. There's no way you can, take your right hand and and make it convert it to your left hand by any translation, that is by moving it, or any rotation. That is, if I take my right hand and I move it or rotate it, it remains a right hand. Okay. Now that's not true for all symmetry operations. If you take a mirror, the mirror operation does change handedness, because let's take your right hand and suppose this is a mirror plane. If you mirror this thing across, you'll create something that looks like this, this, and because this is my left hand. Okay, so anything which is right-handed by mirror operation will change to a left-handed version. And so that's an important distinction between the symmetry elements, whether or not they do or do not change handedness. So the mirror changes the handedness. Now what about an inversion? If you take your right hand and you invert your right hand, what do you end up with? With respect to right hand or left hand? I'm going to ask that as a question on clicker about. I can just ask it. Well, how many say if you take your, we'll do a poll for the right hand. If I invert it, how many say it'll be a right hand? How many say it'll be a left hand? Well, let's try. If you take your right hand and you invert it, so the thumb is pointing up, so what you want the thumb to be pointing down, okay? Your fingers are pointing this way on the right hand, so you want the fingers to point this way. Everything has to be inverted. My palm is facing this way, so the palm should face that way when you invert. And of course, so if you take this thing and you invert it, you end up with something that looks like this. And this is my left hand. Okay. So when you take a right-handed thing and you do an inversion, you actually end up with a left-handed version. So the inversion, like the mirror, changes handedness. Oops. And that becomes important later on when we do these symmetry operations, because of the fact that we do have to be concerned about the handedness, because when we say two things are equivalent, we also have to be concerned whether or not they're equivalent with respect to the handedness. Now, a mirror doesn't pose a problem by itself, because if you have a mirror plane, if you have a point here, and suppose this is a right-handed point, when you go to the other side, this will be a left-handed point. When you come back, it'll be right-handed. So, that's equivalent. Okay. But when you do combinations of rotation and mirrors and so forth, you have to make sure if you start off with a right-handed, when you come back to that point, it should still be right-handed. Okay. Otherwise, you haven't shown. So the equivalency is not only in terms of position; it also needs to be equivalent in terms of handedness. So we're going to start to do the combinations, and let me start off with first of all, a rotation axis. And what we're going to do, there are various ways of considering or proving the different combinations. The method that we're going to use is what is referred to as a repetition pattern. And it's a graphical method to show the equivalency of different combinations of symmetry elements. It's a method which Berger uses in his textbook, and that's why I'm using Berger as a reference. So suppose you have just a simple rotation axis. And the simplest case is a one-fold rotation axis. If you had a one-fold rotation axis, what would the repetition pattern look like? Well, what you do for the repetition pattern is the following. You draw a circle, and in the center of the circle is your rotation axis. So your rotation axis is a one-fold, and you draw a point on the repetition pattern, and you operate upon it by the symmetry element. So if we had a point, this represents a point out in space, okay? And if we rotate it by 360 degrees, it comes back to the exact same point. And that's a repetition pattern, therefore, for a one-fold rotation axis. Just basically one point. I mean, in some sense, everything has one-fold symmetry. Something a little more interesting, suppose we look at a two-fold. What a two-fold repetition pattern would look like is a point here and a point here. A three-fold repetition pattern would look like one here, and one here. A four-fold would look like this. And then the last symmetry that we have is a six-fold, and for the six-fold, what you would have is something that would be here, 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 and here, 60 degrees apart. And in some sense, we've already derived 5 of the 32 point groups. That's 5 of them. You can have a point group with just a 1-fold, which is basically no symmetry. You can have a 2-fold, a 3-fold, a 4-fold, and a 6-fold. What we'll consider, since I'm out of time now, on Friday, is what about if you start combining these? Can you combine them in any way? It turns out you can't. Okay, there's a rule called Euler's rule. It's a rule in solid geometry which imposes a constraint in how you can combine these rotation axes. Okay, so I'll do that on Friday. Thanks.
This concludes MASC 505, Wednesday, August 29, 2007.